Hello everyone, my name is Ali and I'm a PhD student at Carleton University, Ottawa, Canada. Me, along with my colleague Luca Tirel from Sapienza University of Rome, we're gonna present the paper under the name of Action Mask Deep Reinforcement Learning for Controlling Industrial Assembly Lines. The organization of this presentation will be as the following, starting by introduction, literature review, contributions, and then problem formulation, and finally results and discussions. For the introduction, the assembly line balancing problem is a problem of optimizing the distribution of tasks and resources in a manufacturing unit in order to minimize a certain objective function, for example, the product finishing time. In the literature, assembly line balancing problem is a harder class of optimization problem that usually finding its exact solution is a hard mission, especially in big case scenario, so many heuristic solutions have been used. In this paper, the framework of reinforcement learning will be utilized in order to solve the assembly line balancing problem, where the real-time solution of such a problem can significantly reduce the cost in many applications. For example, the assembly line for space launchers, which is a very competitive market. We can see in the following table how the costs have been reduced in the space launchers for the last decades. For the literature review, many authors have tried to implement the deep reinforcement learning framework to solve the assembly line balancing problem. Some of them use only the resource allocation against the time varying load. Another contribution was the usage of parallel training method based on actor-critic deep reinforcement learning, where the authors here used the convolution neural network in order to extract the features of the environment, the factory, without describing briefly the dynamics and the states of the factory and how the agent can provide always a feasible action. In this paper, the contribution will be one, a virtual environment and a mathematical model of a generic industrial assembly line will be used in order to build a virtual environment using OpenAI Gym with all logical constraints in order to train the deep reinforcement learning agents. And then we're going to propose the notion of action mask. Since we have a lot of constraints, many actions will be unfeasible. So the action mask is a tool that will help us to reduce the action space to only feasible actions, thus reducing the computational training time compared to giving a negative reward while doing unfeasible actions. And then finally, we're going to compare the performance of value-based and policy-based agents, value-based like DQN, double and dueling, and policy-based as PPO. And we're going to compare their performance with the exact solution of the optimal control, solving the same exact problem in order to have a baseline to compare with. The problem formulation, in order to describe in a mathematical way the factory, we need to define the following parameters. For example, dk is a time horizon, dw is the number of workstation available, for example, dt is the number of tasks to be done. Another important parameter will be wi, which is the workstation capacities to perform multiple tasks at the same time. For example, if wi is equal to 5, it means that workstation I cannot perform more than 5 tasks at the same time, and the rest of our parameters are shown here. For a state variable, the state of the factory will be a concatenated state of the states number 6, 7, and 8. State number 6 is the state of the workstations, which is the current occupancy of each workstation. State of the task is the duration left for each task. Number 8 is state of the resources, is the remaining amount of resource buffer at a given time. And the concatenated state made by state number 6, 7, and 8 will be the state of the factory. It will be a one vector collecting all the states number 6, 7, and 8. For the control actions, we have two control actions, task action and resource action. Task action will be a matrix of a Boolean variables, 0 and 1, of dimension dw by dt. For example, if we have 3 workstation 5 tasks, we have a control action of 3 by 5. And for example, if the first element is equal to 1 or 0, 1 means that we're going to assign the first task to the first workstation. And the same for the resource allocation. For the constraints, for the sake of clarity of this presentation, we will not briefly describe the mathematical formulation of the constraints here, but are being presented in the paper. But frankly speaking, we are considering the following constraints. For example, we don't assign a finished task. We don't assign a task that is already being in execution state. Or we cannot assign a task that to a workstation that already reached its maximum occupancy. Okay, and the rest of the constraints are stated here. The action mask, an example of the action mask is shown in question number 1, where the length of the action mask will be the same as number of actions available, where each element will be corresponding to a certain action. 0 means unvisible, 1 means visible. So we're going to use this vector in order to pass it to the DQN at a given time k. So we remove, or we assign the q values of unvisible action to be minus infinity. So we will make the DQN agent will not assign, or will never choose an unvisible actions. And the way that we are computing this action mask is represented here in the following algorithm, where we iterate for each action in the action space. We check the visibility of the tasks and resources by the constraints, and if it's feasible, it will take 1. If it's not visible, it will take 0. Okay. For the reward function, we have the following reward function, where its motivation is to give a more reward when we finish in a less time. So for example, the less the k, the more the reward. So when the agent is trying to finish in a less time, it will take a much more reward. And alpha and beta are such tuning parameters that we're going to choose in order to have a better performance in general. For the proposed control architecture, we can see here finally the control architecture in the framework of deep reinforcement learning, where the factory of the environment will pass the next reward and state to something that is called the action masker, which will check the visibility of the tasks and resources and pass an action mask at every given time, in such a way that it will be given to the DQN agent, where we are assigning to the unvisible actions a q value, for example, in the DQN to minus infinity, and for the PPO policy-based algorithm to have a probability of the unvisible action to be equal to 0, such a way that the agent will always apply a visible actions. For the results, we see in the following figure number 3 a comparison between the effect of having a PPO agent with a mask and without a mask. With a mask, we can see that we are converging to the optimal solution solved by optimal control problem, that is the optimal value of the finishing time is 9. And we can see that the PPO agent with an action mask is being converged to the optimal solution, while with the case without an action mask is not converging to the optimal solution, since it can easily apply unvisible actions, leading to not learning how to finish in a proper time. In figure 4, we see that the comparison of DQN agents, where we can see that we're also converging to the optimal solution, which is 9. In all the DQN agents, for example, we can see the doubling DQN is being converged in almost 1,500 episodes to the optimal solution. Computational time of a training, you can see here all the simulations have been performed in the following hardware, and we can see in table 2 a comparison of the training time between the agents. We can see that the action masked BBO is being like 10 times faster of the DQN agents, and we can see also that is being converged in a less time, convergence less episodes, for example 280. And we can see also the calling time of the solution after training, and that's the take-home message, where yes, in the deep reinforcement learning solutions we can train in a much more time compared to the optimal solutions, but when we want to call the solution, it will be in terms of milliseconds, okay, which will provide a real-time implementation of such environments. So the conclusion that the adoption of the action mask dramatically improves the training time of all of the agent, either value-based or a policy-based. We conclude that the action mask PPO algorithm shows a great potential in many aspects, in optimality and stability of solution, in fast computational time and fast training time, and also that the deep reinforcement learning framework, the trained agent can directly compute the solution, providing a real-time solution of the problem. And that is the reference that we used in this presentation, and thank you.